Life from outer space, cosmic molecules, and the origins of life. Scientists believe that the origins of life on Earth may have come from outer space and could be prevalent throughout the universe. In a groundbreaking discovery, researchers found complex organic molecules in a disk surrounding a protostar. These molecules are considered precursors to the building blocks of life, which eventually transform into sugars and amino acids, forming the intricate flora and fauna that surround us. Although such molecules have been found in other locations before, this new finding fills in a previously unknown missing link, suggesting that life may be more abundant than we realize. The formation of a young star from a cold protostar, encircled by dust and gas, involves intense radiation and gas ejection. Scientists were concerned that this extreme process could reset the chemical compounds around the star, necessitating their reformation in the disks that simultaneously create planets. However, the new research indicates that complex molecules can survive this process and be inherited by the subsequent disks. The study, titled A Deep Search for Complex Organic Molecules Toward the Protoplanetary Disk of V883 Ori, is published in the Astrophysical Journal Letters. But here's where it gets controversial. If life on Earth indeed originated from outer space, what does this mean for our understanding of the universe and our place in it? This discovery could spark a heated debate among scientists and the general public alike. What do you think? Let us know in the comments below. The cosmic origins of life. Molecules from space reveal surprising secrets. The origins of life on Earth might not be solely terrestrial. They could have cosmic roots. Astronomers have made a groundbreaking discovery, finding complex organic molecules, the building blocks of life, in a planet-forming disk. This suggests that life's evolution may have begun in outer space, challenging our understanding of the universe. The building blocks of life in space. In a young stellar system, VAA3 Orionis, astronomers using the Atacama Large Millimeter Submillimeter Array, ALMA, detected signatures of complex organic compounds. These include ethylene glycol and glycolitrile, potential precursors to sugars and amino acids. This is the first tentative detection of such molecules in a planet-forming disk, and it hints at a universal process in the origin of biological molecules. A cosmic chemical evolution. Findings indicate that chemical evolution doesn't start with the formation of planets. Instead, protoplanetary disks inherit and further develop complex molecules from earlier evolutionary stages. This means that the building blocks of life could be widespread throughout the universe, not limited to local conditions. And all this possible if these precursors are indeed prevalent, the probability of finding them on fully formed planets increases. Whether life develops on these planets depends on external factors, but the potential for life to exist elsewhere just got a whole lot more intriguing. The evolution of complex molecules. Astronomers have previously discovered complex organic molecules, COMs, in various cosmic environments associated with planet and star formation. The discovery of 17 COMs, including ethylene glycol and glycolitrile, in the protoplanetary disk of V883 Orionis, provides a crucial link in the evolution of these molecules. Glycolitrile, for instance, is a precursor to essential biological components like amino acids and nucleobases. A straight line of chemical enrichment. The transition from a protostar to a young star with a protoplanetary disk is a violent phase, with intense radiation and rapid gas ejection. Scientists previously thought this phase might destroy complex chemistry. However, the new findings suggest the opposite. Protoplanetary disks continue to develop complex molecules, and the conditions that predefine biological processes could be widespread, not limited to individual planetary systems. A cosmic chemical evolution. Chemical reactions that synthesize COMs occur under cold conditions, often on icy dust grains. These molecules remain hidden in mixtures of rock, dust, and ice until external heating evaporates the ice, releasing them. In the V883 Orionis system, the central star's growth and radiation heat the surrounding disk, revealing the complex molecules and the future of discovery. While this discovery is exciting, there's still much to uncover. Higher resolution data will confirm the detections and potentially reveal even more complex chemicals. Additionally, exploring other regions of the electromagnetic spectrum might lead to the discovery of even more evolved molecules. The universe continues to surprise and inspire, and the search for the origins of life is an ongoing, captivating journey. Conclusion. The study, led by Abubakar Fadul from the Max Planck Institute for Astronomy, MPIR, involved a team of astronomers who utilized ALMA's capabilities to make this groundbreaking detection. The findings were published in the Astrophysical Journal Letters, contributing to our understanding of the universe and the potential for life beyond Earth. Life on Earth may have started in space. Organic molecules discovered. Imagine this. The spark of life on Earth may not have originated here at all. What if the very building blocks that allowed life to emerge were delivered from the vastness of space? This thought-provoking idea is supported by new evidence suggesting that the ingredients for life could be widespread across the cosmos. Let's dive into how scientists are uncovering these clues and what they mean for our understanding of life's origins. At the heart of this discovery is a young star named V883 Orionis, located roughly 1,305 light-years away in the constellation Orion. Astronomers using the Atacama Large Millimeter Submillimeter Array, ALMA, have detected complex organic molecules, COMS, swirling within the protoplanetary disk surrounding this budding star. These molecules are just random assortments of atoms. They include ethylene glycol and glycol nitrile, both of which play vital roles in forming the chemical structures found in DNA and RNA. But here's where it gets fascinating. Ethylene glycol, a sugar alcohol commonly associated with antifreeze, isn't something you'd want to drink. It's toxic, but it holds enormous significance as a prebiotic molecule, meaning it has the potential to pave the way for life. Glycol nitrile, meanwhile, contributes to the creation of adenine, one of the essential components of genetic material. Together, these findings hint at the possibility that similar processes might have occurred billions of years ago during the formation of our own solar system. The detection of these molecules didn't come easily. The team, led by astronomer Abubakar Fadul from the Max Planck Institute for Astronomy, focused on the warm inner regions of the protostar's envelope, rather than its fully formed protoplanetary disk. Why does this matter? Because the dense cloud material enveloping the star plays a critical role in the formation and preservation of COMS. It turns out that even violent phases of stellar development, such as the intense radiation and gas ejections associated with accretion bursts, don't necessarily destroy these delicate compounds. Instead, they can persist and continue to evolve. And this is the part most people miss. The implications go far beyond V883 Orionis itself. Scientists believe that comets, those icy remnants of planetary formation, may have once ferried similar organic molecules to Earth. Picture this. Billions of years ago, when the solar system was still chaotic and filled with collisions, comets bombarded our planet, potentially depositing the raw materials needed for life. Could these ancient impacts have seeded our world with the precursors to biology? The question remains open but tantalizing. What makes this study particularly intriguing is the method used to identify these molecules. By observing V883 Orionis at radio frequencies, researchers confirmed the presence of ethylene glycol and glycol nitrile. But they're not stopping there. They suspect that many more COMS are lurking in the shadows, waiting to be discovered through observations in other spectral bands. In fact, higher resolution data could reveal even more sophisticated chemicals, offering deeper insights into the cosmic origins of life. While we're thrilled with what we've uncovered so far, says Camber Schwartz, a co-author of the study, there's still much to learn. Higher resolution observations will help us confirm these detections and possibly uncover entirely new molecules. This research raises profound questions about the nature of life in the universe. If COMS are common in star-forming regions, does that mean life could arise elsewhere under the right conditions? Or are we truly alone? As telescopes advance and our ability to probe the cosmos improves, the answers may lie closer than we think. So what do you think? Do you believe life's beginnings trace back to interstellar chemistry? Or is there another explanation we haven't considered yet? Join the conversation below.